Hi everyone. In the last two lectures we have discussed about the spectral family generated by self-adjoint operators and its property. Today we are going to discuss about the spectral theorem for self-adjoint operators. Earlier we have seen the spectral theorem for compact self-adjoint operators. Now we want to drop the condition, namely compactness, and see how the representation of a self-adjoint operator look like. So before going into discussion, let us quickly recall about the properties of spectral family generated by a self-adjoint operator. So if T is a self-adjoint operator, we have defined E lambda as projection onto null space of T lambda plus, where T lambda is nothing but T minus lambda I, and T lambda plus is modulus of T lambda plus T lambda by 2, and E lambdas are projections onto or null space of T lambda plus, and we have shown that E lambda is 0 when lambda less than empty, the lower numerical bound, and lambda when lambda is bigger than or equal to the upper numerical bound, capital M suffix T, then E lambda is identity, and when A commutes with T, then E lambda also commutes with T. In particular, all E lambdas commutes with E mu, where lambda and mu are in R. Whenever lambda 1 less than or equal to lambda 2, we have shown that E lambda 1 less than or equal to E lambda 2, and E lambda 1, E lambda 2 is E lambda 1. And similarly, when lambda 1 less than or equal to lambda 2, we have shown that lambda 1 into E lambda 2 minus E lambda 1 less than or equal to T into E lambda 2 minus E lambda 1, that is less than or equal to lambda 2 times E lambda 2 minus E lambda 1. So these are the properties of spectral family generated by a self-adjoint operator. Now we want to integrate with respect to a spectral family generated by a self-adjoint operator. So if you have a family of projections E lambda, then we define integral A to be f lambda d E lambda to be the limit of Riemann Stieltjes sum of the form summation I equal to 1 to n f lambda I hat E lambda I minus E lambda I minus 1, where lambda I hat is a member in the ith subinterval lambda I minus 1 comma lambda I. So the meaning of this is that given any epsilon positive, there exists a delta such that for any partition P of AB such with norm of P less than delta, and for any choice of lambda I hat in this ith subinterval, we have that operator norm of A minus I equal to 1 to n f of lambda I hat multiplied by E lambda I minus E lambda I minus 1 is strictly less than epsilon. And here the operator A is nothing but integral A to be f lambda d E lambda, and this convergence is with respect to the operator norm of B of H. Okay, now today we want to discuss about the spectral theorem. Let T be a self-adjoint operator defined on Hilbert space H. Then there exists a family E lambda in R of orthogonal projections satisfying the following conditions. The first one is lambda 1 less than or equal to lambda 2 implies E lambda 1 less than or equal to E lambda 2. The second condition is E lambda equal to 0 when lambda less than the lower numerical bound of T. It is identity when lambda bigger than or equal to the upper numerical bound capital M suffix T. If AT equal to TA, then A E lambda commutes with A E lambda equals to E lambda A. The fourth condition is E lambdas are right continuous. That means limit lambda tends to lambda naught, lambda are bigger than lambda naught, E lambda x is nothing but E lambda naught x for every x in H. And fifth condition is that if you integrate with respect to E lambda, that is T can be obtained by integrating over spectrum of T, or we can say that integration from A to B lambda d lambda where A is a real number less than m suffix t and B is a real number bigger than or equal to capital M suffix t. And the integration we have already explained the meaning of this integration, and the right hand side operator converges to T in the operator now. So this is called the spectral theorem for self-adjoint operators. And we have already seen there exists a family of projections satisfying 1, 2 and 3. So the proof okay. So we want to find a family of orthogonal projections satisfying these conditions, but we have already seen if you look at E lambda to be orthogonal projection onto null space of T lambda plus, we have seen that they satisfy 1, 2, 3 conditions. So let us define E lambda to be orthogonal projection onto null space of T lambda plus. So recall T lambda is T minus lambda I, T lambda plus is mod T lambda plus T lambda by 2. And we have seen that E lambda satisfy the conditions 1, 2 and 3. We have seen that E lambdas satisfy these 3 conditions. So let us quickly recall. So we have seen that if you take E lambda to be orthogonal projection onto null space of T lambda plus, in lemma 2 we have shown that E lambda is 0 when lambda less than small m suffix t, and identity if lambda is bigger than or equal to capital M suffix t. And we have shown that if A commutes with T, then E lambda also commutes with A. And in the other lemma we have shown that the monotonic property E lambda 1 less than or equal to lambda 2 whenever lambda 1 less than or equal to lambda 2. Okay. Okay, so the first property is known as monotonic property, and the third one is commutative property. The second property says that E lambdas are supported on the spectrum of T, because we know that spectrum of T is contained in the closed interval small f m suffix t comma capital M suffix t. And the fourth condition is known as right continuity. Okay. Now we want to show that the fourth and fifth conditions are satisfied. Let us look at the proof of 4. So let us take lambda bigger than or equal to lambda naught. Then we have E lambda naught is less than or equal to E lambda. So we already know that these E lambdas are bounded by identity. So E lambda naught is bigger than 0. That means and we know that E lambdas are increasing and they are bounded by the orthogonal projection, namely identity operator. By the monotone convergence theorem, we can show that this E lambda converges to some operator which is self-adjoint operator with respect to the strong operator topology. So by the monotone convergence theorem, we have shown that monotone convergence theorem takes place for sequence of self-adjoint operators bounded above by some self-adjoint operator, but the same proof works for a net of operators also. So there exists some A in B of H such that E lambda x limit E lambda x lambda decreases to lambda naught. This is A of x for every x in H. But we want to show that this limit must be E lambda naught. So our claim is the following: A equal to E lambda naught. Now we know that lambda naught less than or equal to lambda implies lambda naught multiplied by E lambda minus E lambda naught. This is less than or equal to T into E lambda minus E lambda naught, and this is less than or equal to lambda times E lambda minus E lambda naught. This we have shown in lemma 4. So if you look at this condition, we can actually show that we can conclude that T minus lambda naught I into E lambda minus E lambda naught is bigger than 0, and this implies as lambda going to lambda naught, we can actually conclude that. So that means this operator, when you take inner product x with operator acting on x with inner product x is positive. That is T lambda naught E lambda minus E lambda naught. This is positive for every x in H. This implies, but we know that E lambda converges to A in the strong operator topology. This is T lambda naught A minus E lambda naught x. X is positive. That means we can say that this operator T lambda naught multiplied by A minus E lambda naught is always positive. So let us call this inequality as 1. Now if you look at the second inequality that we are having here, so let us call this is star and this is double star. So we can say that by the inequality double star, so we have that lambda I minus T multiplied by E lambda minus E lambda naught acting on x, inner product x with this is positive for every x in H. Now as lambda going to lambda naught, we know that E lambda x converges to Ax. So this implies lambda naught identity minus T into A minus E lambda naught x inner product x for every x in H. So this implies minus of T lambda naught into A minus E lambda naught is always bigger than 0, or we can say that T lambda naught into A minus E lambda naught is less than or equal to 0. So let us call this inequality by 2. So in the first inequality we have concluded T lambda naught into A minus E lambda naught is positive. In the second inequality we have shown that the same operator is negative. Hence by 1 and 2 we can say that the operator must be 0. By 1 and 2, so we get T lambda naught into A minus E lambda naught is 0. Okay. Now consider, if you look at T lambda naught plus into A minus E lambda naught, this can be written as, we know that T lambda naught plus is nothing but T lambda naught into I minus E lambda naught. So this is T lambda naught into I minus E lambda naught multiplied by A minus E lambda naught. So this we know that E lambda naught and I minus E lambda naught commutes with T lambda naught. So we can say that this I minus E lambda naught into T lambda naught multiplied by A minus E lambda naught. But we know that A minus E lambda naught is 0. So on the whole this is a 0 operator. So this implies that range of the operator A minus E lambda naught is contained in null space of T lambda naught plus. But null space of T lambda naught plus is nothing but this is range of E lambda naught. So let us call this as inclusion 3. Okay. Now we have E lambda naught into E lambda is E lambda naught. So as lambda naught is less than or equal to lambda. Okay. So this implies E lambda naught into E lambda minus E lambda naught is 0, because we can write E lambda naught equals to E lambda naught square, because it's an orthogonal projection. So this implies when we take limit lambda going to lambda naught, E lambda naught into E lambda minus this is also 0. So now we know that E lambda converges to A. So this implies E lambda naught multiplied by A into E minus lambda naught is 0. Okay. But we know by the inclusion 3, range of A minus E lambda naught is contained in range of E lambda naught. So now this part, so range of this is contained in range of E lambda naught. That means on range of A minus E lambda naught acts as an identity operator. So from this we can say that A minus E lambda naught is 0, or we can say that A equal to E lambda. So here the convergence is with respect to strong operator topology. So we can say that A equal to E lambda naught, because this happens for every x in H. Okay, so this completes the proof of the fourth statement. Now we want to look at the spectral representation of T using this Riemann-Stieltjes-like integral. So let us look at the proof of fifth one. So we want to approximate T by so let us start with some epsilon positive. So we want to approximate T by operators of the form summation I equal to 1 to n lambda I hat E lambda I minus E lambda I minus, where this lambda I hat is in the interval lambda I minus 1 comma lambda I, and I equal to 1 to n. Okay, so let us take epsilon positive, and let us take A less than empty and B bigger than or equal to capital MT. So let us take a partition P equal to lambda naught A, lambda 1, so on, lambda n equal to B, be a partition of the interval A comma B. So we want to show that norm of T minus summation I equal to 1 to n lambda I hat multiplied by E lambda I minus E lambda I minus 1 is less than epsilon, where lambda is are in the subinterval lambda I minus 1 comma lambda I, and we want to find a delta bigger than 0 such that whenever P is a partition with mod norm of P less than delta, then this should happen. Okay, that means we want to show that now T is a self-adjoint operator, and the operators in this summation, they are also self-adjoint. So it is enough to look at epsilon I minus summation this is minus epsilon less than or equal to minus epsilon I less than or equal to T minus summation I equal to 1 to n lambda I multiplied by E lambda I minus E lambda I minus 1, this is less than or equal to epsilon times identity. This is what we want to show. Okay, now so note that if you look at summation I equal to 1 to n lambda I hat, here I lambda I hat E lambda I, if you look at summation I equal to 1 to n E lambda I minus E lambda I minus 1, we will get E lambda n minus E lambda naught, that is EA. So this is nothing but we get EB minus EA. When lambda is bigger than or equal to B, we know that E lambda is identity. When lambda is less than or equal to lambda is less than m suffix t, then E lambda is 0. Now we know that A is less than the lower numerical bound and B is bigger than or equal to upper numerical bound, so we will get I minus 0. This is an identity operator. Okay, now using this we want to prove this result. Okay, so let us look at so we want to consider T minus summation I equal to 1 to n lambda I hat e lambda I minus e lambda I minus 1. This is nothing but we can say that is t summation I equal to 1 to n e lambda I minus e lambda I minus 1. So because this summation is identity operator, this is some minus summation I equal to 1 to n lambda I hat e lambda I minus e lambda I minus 1, and this we can write as summation I equal to 1 to n t minus lambda I hat identity. Okay, so instead of writing this, we can actually use the following result. So lambda I minus 1 less than lambda I, this implies lambda I minus 1 into e lambda I minus e lambda I minus 1 less than or equal to t into e lambda I minus e lambda I minus 1. This is less than or equal to lambda I into e lambda I minus e lambda I minus 1. This result we know. Okay. Now this is true for every I. So from that we can say that t is less than or equal to lambda I. So we can say that this is less than or equal to, now you take the summation, we can take the summation also, I equal to 1 to n summation. So if you look at, now using this we can say that the above first operator is less than or equal to summation I equal to 1 to n lambda I e lambda I minus e lambda I minus 1 minus summation I equal to 1 to n lambda I hat e lambda I minus e lambda I minus 1, and this is nothing but summation I equal to 1 to n lambda I minus lambda I hat into e lambda I minus e lambda I minus 1. Okay, now we want to show that this is less than epsilon times identity. Now given any epsilon positive, we want to find a delta bigger than 0, such that whenever norm of p less than delta, then norm of t minus summation I equal to 1 to n lambda I hat e lambda I minus e lambda I minus 1 less than epsilon. So that means we have to choose a delta, but on the whole we want to show this is less than epsilon times identity. But we know that if this is less than epsilon, then remaining summation is identity operator. So that means if we choose delta equal to epsilon, so then we can say that t minus summation I equal to 1 to n lambda I hat e lambda I minus e lambda I minus 1 is less than or equal to, so norm of the partition is less than delta, implies this this is less than epsilon into summation I equal to 1 to n e lambda I, this is epsilon identity. So here we have to choose, assume that norm of the partition, that is look at maximum of the length of lambda I minus 1 less than I less than n, this is less than delta. Then we can say that. Okay. Now in the similar way we can actually show that. So we have shown so far this inequality. Now using the same trick we can show that the other inequality also holds true. That means this inequality also holds true. So from these two inequalities we can conclude that, therefore, so similarly we can show that summation I equal to 1 to n lambda I hat e lambda I minus e lambda I minus 1 is bigger than minus epsilon times identity. Here we have used the fact that t is less than or equal to lambda I, this second inequality in this whole thing. So if you use the first one you will get the other one, t minus summation I equal to 1 to n lambda I hat multiplied by e lambda I minus e lambda I minus 1 is bigger than minus epsilon. Therefore norm of t minus summation I equal to 1 to n lambda I hat e lambda I minus e lambda I minus 1 is less than epsilon, and this is true for all choices of lambda I hat in the ith subinterval lambda I minus 1 comma lambda I. By the definition of the integral we can conclude that we can integrate lambda d lambda on the interval ab to get t. Okay, this is the spectral representation of t. Okay, now one can ask the question whether this family of projections that we are integrating with to get the self-adjoint operator, is this family unique? So in fact we can show the uniqueness by using the right continuity part. By using the fourth condition we can show that if there exists another family of projections satisfying all these conditions, we can show that that family coincide with projection onto null space of t lambda plus. So we define a spectral family we have defined spectral family for a self-adjoint operator. A spectral family for a Hilbert space H is a function from R to B of H. So we can say that E lambda such that the following conditions are satisfied. So E lambda is an orthogonal projection for each lambda in R. Lambda 1 less than or equal to lambda 2 implies E lambda 1 less than E lambda 2. This is a monotonic property. The third one is right continuous. Okay, so before that we can say that E lambda, when lambda going to minus infinity, this is 0, limit lambda going to plus infinity, E lambda is identity operator. This limit is with respect to the strong operator topology, that is x for every x in H. And the fourth condition is right continuity. E lambda converges to E lambda plus, so limit E lambda epsilon going to 0, E lambda goes to E lambda at every point x. So here epsilon is positive. So this is called right continuity. Okay. So if a family of projections satisfy these four conditions, we call this a spectral family for a Hilbert space H. And we have shown that if T is a self-adjoint operator, there exists a family of projections satisfying all these properties. And we can also show that if there is a spectral family, if there is another spectral family which satisfies these conditions 1, 2, 4 and 5, then we can show that that spectral family coincide with projection onto null space of T lambda plus. Okay. So if T is a self-adjoint operator, if then there exists a unique spectral family E lambda for H such that T can be written as inter A to B lambda d lambda, where A less than empty and B bigger than or equal to okay. So this can be proved using the right continuity property. Okay. Now that means once this result is true, we can show that we can always take the spectral family to be projection onto null space of T lambda plus to get the operator T. Okay. So this is the spectral theorem for self-adjoint operator. In the next class we discuss about few examples, and later we discuss about continuous functions of self-adjoint operator. I'll stop here. Thank you very much.